Today we're going to talk about confidence intervals for one-sample proportions. Recall that the sampling distribution model of p hat is centered at p with a standard deviation of the square root of pq over n. Since we don't know p, we can't find the true standard deviation of the sampling distribution model, so we need to find the standard error. And we'll use the standard error for p hat equaling the square root of p hat q hat over n. By the 68, 95, 99.7% rule, we know that about 68% of all samples will have p hats within one standard error of p. About 95% of all samples will have p hats within two standard errors of p, and about 99.7% of all samples will have p hats within three standard errors of p. We can look at this from p hats' point of view. Consider the 95% level. There's a 95% chance that p is no more than two standard errors away from p hat. So if we reach out two standard errors, we are 95% sure that p will be in that interval. In other words, if we reach out two standard errors in either direction of p hat, we can be 95% confident that this interval contains the true proportion. This is called a 95% confidence interval. So in the middle here we have p hat, and we go two standard errors to the right and left, we'll be 95% confident. Each confidence interval uses a sample statistic to estimate a population parameter. But since samples vary, the statistics we use, and thus the confidence intervals we construct, vary as well. The figure to the right shows that some of our confidence intervals capture the true proportion, the green horizontal line, while others do not. Our confidence is in the process of constructing the interval, not in any one interval itself. Thus, we expect 95% of all 95% confidence intervals to contain the true population parameter that we are estimating. So in other words, if you take this first interval here, you can see that it does not contain the true population proportion. The second one does. The probability that we have the true population proportion is either 0 or 1. It's either in the interval or it's not in the interval. We can claim with 95% confidence that the interval p hat plus or minus two standard errors contains the true population proportion. The extent of the interval on either side of p hat is called the margin of error. In general, confidence intervals have the form estimate plus or minus margin of error. The more confident we want to be, the larger our margin of error needs to be. So if we go three standard deviations, we are 99.7% confident. To be more confident, we wind up being less precise. We need more values in our confidence interval to be more certain. Because of this, every confidence interval is a balance between certainty and precision. The tension between certainty and precision is always there. Fortunately, in most cases, we can be both sufficiently certain and sufficiently precise to make useful statements. The choice of confidence level is somewhat arbitrary, but keep in mind this tension between certainty and precision when selecting your confidence level. The most commonly chosen confidence levels are 90%, 95%, and 99%, but any percentage can be used. The two in p hat plus or minus two standard errors, our 95% confidence interval, came from the 68, 95, 99.7% rule. Using a table or technology, we find that a more exact value of our 95% confidence interval is 1.96 instead of 2. We call 1.6 the critical value and denote it Z star. For any confidence level, we can find the corresponding critical value. For example, for a 90% confidence interval, the critical value is 1.645. All statistical models depend on assumptions. Different models depend on different assumptions. If those assumptions are not true, the model might be inappropriate and our conclusions based on it may be wrong. You can never be sure that an assumption is true, but you can often decide whether an assumption is plausible by checking a related condition. Here are the assumptions and the corresponding conditions you must check before creating a confidence interval for proportion. The independence assumption. The data values are assumed to be independent from each other. We check three conditions to decide whether independence is plausible. Is there any reason to believe that the data values somehow affect each other? This condition depends on your knowledge of the situation. You can't check it with data. Were the data sampled at random or generated from a properly randomized experiment? Proper randomization can help ensure independence. Is the sample size no more than 10% of the population? Sample size assumption. Sample needs to be large enough for us to be able to use the central limit theorem. So we must expect at least 10 successes and at least 10 failures. When the conditions are met, we are ready to find the confidence interval for the population proportion P. The confidence interval is p hat plus or minus z star times the standard error, where standard error is equal to the square root of p hat q hat over n. The critical value z star depends on the particular confidence level C that you specify. Let's take an example. A survey of 865 voters in one state reveals that 408 favor approval of an issue before the legislature. Construct a 95% confidence interval for the percentage of all voters in the state who favor approval. So there are 3 steps. The first step is that we're going to check our assumptions and conditions. So we have a simple random sample and we will have to assume that. Population size is greater than 10 times the sample size of 865. We can safely state that. And that NP hat, and notice it's going to be P hat and not P, since we don't know P, we have to use P hat. It's 865 times 408 over 865, which gives us 408, and that's greater than or equal to 10. And NQ hat is 865 times 457 over 865, which equals 457, which is greater than or equal to 10. Step 2, we're going to calculate the confidence interval. So here's our formula. Plugging in our values, we have 408 over 865 for p hat. Since it's 95% confidence, we're going to use 1.96 for z star. And our standard error is 408 over 865 times 457 over 865 divided by 865 and take the square root of that. So we get 0.438 and 0.505. Our third step is the conclusion. We are 95% confident that the true population proportion of voters that favor approval of an issue is between 43.8% and 50.5%. So what I've given you is a boilerplate, but I've used it in context of the problem. Let's take another example. 92 adults selected randomly from one town. 60 have health insurance. Construct a 90% confidence interval for the percentage of all adults in the town who have health insurance. Step 1, checking our assumptions and conditions. We have a simple random sample and it's stated. Population size is greater than 10 times 92. And NP hat, which is 60, and NQ hat, which is 32, they're both greater than or equal to 10. Calculate the confidence interval for step 2. Our formula. So P hat is 60 over 92. Since we're doing a 90% confidence interval, we're going to use 1.645 times the standard error, which is the square root of 60 over 92 times 32 over 92 divided by 92. We get for our interval 0.571 to 0.734. So our conclusion is we are 95% confident that the true population proportion of adults that have health insurance is between 57.1% and 73.4%. Don't misstate what the interval means. Don't suggest that the parameter varies. Don't claim that other samples will agree with yours. Don't be certain about the parameter, and don't forget it's the parameter, not the statistic, that we're estimating. Don't claim to know too much. Do take responsibility for the uncertainty. We can't be exact, but how precise do we need to be? One way to make the margin of error smaller is to reduce the level of confidence. This may not be a useful solution. You need to think about your margin of error when you design your study. To get a narrower interval without giving up confidence, you need to have less variability. You can do this with a larger sample. So in general, the sample size needed to produce a confidence interval with a given margin of error at a given confidence level is n equals z star squared times p hat q hat over the margin of error squared, where z star is the critical value for your confidence level. To be safe, round up the sample size you obtain. So taking an example, an advertising firm wants to confirm estimates that 24% of the households will buy something on the internet next year. What sample size will produce a margin of error of 9% with 90% confidence level? So here's our formula for sample size. Plugging in our numbers, since we want to be 90% confident, we're going to use 1.645. Our p hat is 0.24. Our q hat is going to be 0.76, and our margin of error is 0.09. So we get 60.94. Rounding up gives us 61. Next example. A pollster wishes to estimate the true proportion of U.S. voters who oppose capital punishment. How many voters should be surveyed in order to be 95% confident that the true proportion is estimated within 3%? So our formula for sample size. Our z star is going to be 1.96 since we're 95% confident. Now you'll notice that p hat and q hat are 0.5. The reason being is that we don't have a p hat or a q hat in this problem. So to be on the safe side or the conservative side, we're going to estimate it to be 0.5. Our margin of error is 0.03. So solving, we get 1067.11. Again, we're going to round up, so our sample size is 1068. A poll of 2017 likely voters indicated that 70% would vote in favor of a proposed constitutional amendment. The margin of error for this poll was 2%. What is the confidence level? So here I'm going to use the sample size formula. I know my sample size is 2017. I'm looking for z. The reason I'm going to look for z is that's going to help me find the confidence level. Our p hat is 0.7, our q hat is 0.3, and our margin of error is 0.02. 0.8068 equals 0.21 z squared. Dividing by 0.21 and then taking the square root, I'm going to get z equals 1.96. So we recognize this number as a 95% confidence. So what have we learned? We have learned to use a sample to say something about the world at large. This process is based on our understanding of sampling models and will be the focus for the rest of the book. In this chapter, we learned how to construct a confidence interval for a population proportion. And we learned that interpretation of our confidence interval is key. We can't be certain, but we can be confident.